So we have seen what a Riemannian symmetric pair is. I forgot to mention one important definition. So this is the definition of effective. Okay. So suppose G is acting on a manifold, a Lie group is acting on a manifold, and suppose so G to the group of diffeomorphism, I have a map acting on the left, G going to LG. So this is an abstract group homomorphism, and the kernel. So G action. So yeah. So if G is acting transitively, and if then for any point M0, kernel of this map, kernel of let's call it phi. You can see that this is G stabilizer M0, G inverse, G in G, which is the greatest normal subgroup. So I'm assuming under this assumption, so of G in. Okay. So G action is said to be effective if this, in general, G action is said to be effective if this kernel is identity, or in other words, G sits inside the diffeomorphism group. And in this case, you can see that the G action, so G action is said to be effective if G is, if kernel is identity, and in case G is acting transitively, G, then G is effective if and only if the greatest normal subgroup of G sitting inside stabilizer of M0 is identity. If and only if the maximal of normal subgroup G in is trivial. Okay. So in our case, we have a situation where G is acting effectively, and the kernel of this action is K. The kernel of this action is precisely and stabilizer of EK is K. So G is said to be the Riemannian symmetric pair GK sigma is said to be effective is if the maximal normal of G in K is trivial. Okay? And if you start with a Riemannian symmetric pair, and if you go modulo the kernel of this action, then you land up in the same symmetric space. So there is no harm in assuming from the beginning that we start with the effective Riemannian symmetric pair. Okay, so from now on, our symmetric pair is going to be effective symmetric pair. Okay. All right. So and let us just go through some examples again that we have seen symmetric spaces. We have so we have seen Rn. I'm just going to list quickly what are the Riemannian symmetric pair for all these objects, and then we'll see something new. And so the Riemannian symmetric pair that we obtain for this symmetric space Rn is, my G is going to be semi-direct product of full isometric group, which is SON, connected component of the isometric group is SON semi-direct product of Rn, which can be also identified with this following linear group. So this is A alpha, or maybe A1, 0, A is in SON, A is in Rn. Here Rn is thought to be a column vectors. And this is a group, and in this case my sigma is going to be A0, 1 is going to be, just follow the process. The way I constructed Riemannian symmetric pair from a symmetric space, if you follow the process, you will see that you can identify that symmetric pair with the following symmetric pair that I'm going to write. So this minus A1, this is the definition, and my on P is going to be simply, if you see, so these are linearly groups. So P, if you identify, this is going to be 0, A, 0, 1, A is in Rn, sorry, 0, A is in Rn, and my inner product on this is just going to be, so just defined to be the usual, these are column vectors, so this is A dot B. Okay, usual inner product in Rn is my definition. So this you can check. So this check that this is really, this is the Riemannian symmetric pair. For Sn, I have to take G to be SON plus 1, and here you can see that K is A1, 0, 0, A is in SON, here K is going to be SON, and SON is sitting inside SON plus 1 as, you know, A1. So that way I identify SON in sitting inside SON plus 1 in many ways, at least 2 different ways that one can think of immediately. But this is the embedding that I'm taking. And this is I'm taking because I'm here considering En plus 1. My reference point that I consider here is En plus 1 is my P. And the stabilizer of En plus 1 is just going to be a matrix of this form, because it's an orthogonal matrix. It keeps En invariant, so it keeps the orthogonal complement of that invariant. So this is going to be of this form. So P is this, and if we recall, our sigma P V was what was it? 2 VP minus P minus V. And if you write down, so this is an element of SON, and if you with the standard basis, if you write the matrix, this is going to be with respect to the standard basis, this is going to be a matrix of the form minus IN1. This is an element in ON plus 1. And You recall that this was, I was conjugating, I had this is the symmetry. Symmetry is a linear map here, and symmetries are like identified with elements of ON. This is an element of ON plus 1. And I was conjugating, the way I was considering constructing the automorphism inside G was to conjugate by the symmetry at the reference point here. The reference point is E plus. And this, so you conjugate by this, and if you conjugate, we'll land up the P is going to be something like 0 A minus A of this form. And then, so one thing one should always remember, that the following map, so always remember that if I am given the MNR, then AB going to trace of A BT gives me an inner product. Okay? So I just restrict that trace MNR Mn plus 1 here. So always when I'm giving the matrix this is an inner product, because it's very easy to check it is an inner product. And so it's a positive definite form, and it's, something is 0 if AA is 0 if and only trace of AA transpose is 0. So you restrict this form over here, and you will get the required form that I am talking about. And this form is always invariant under the corresponding SON group, so it will be okay. So let's talk about the third one, HN. HN, my connected component of the isometric group is SON1 connected component. And SON, so SON again sits here as A going to A100, okay? And my P is, I have taken a hyperboloid model of this HN, so I'm working with that model, and my En plus 1, and again you recall that sigma P, what was it? Sigma P was minus 2P V P minus V. So with respect to the standard basis, matrix of sigma P is going to be again 1 and again minus In. And you conjugate again by this to this group, and you will end up that this is exactly satisfying the component. And again do the same thing, restrict trace to, so, and when you conjugate on the Lie algebra of SON minus 1, you take the minus 1 eigenspace and call it P, and similarly restrict this on P, and you'll get the required Riemannian symmetric pair. Okay, so now so these are all constant curvature spaces. So we'll see a new Riemannian symmetric pair, which is not falling on this category, which is also, so given any Lie group, and Riemannian symmetric pair starts with a Lie group, a compact subgroup, and a involution, and the inner product, blah, blah, blah. So we don't need to we can, out of this data, we construct it. So let us take a special case which is playing a very important role in the previous lectures of Pranab, Sardar, and so on. So here, G is SLNR, K is SONR, my sigma A is A transpose inverse, okay, and my this on P is, again, you just restrict the trace. So what is, so K, the Lie algebra of K is the matrices of skew symmetric matrices, and P is going to be symmetric matrices. So restrict restrict the form trace, so restrict trace A, B going to trace A, B transpose on P, and since it is symmetric, and since AB is in P, this is going to be just simply trace of AB. Okay, on P. So this gives me a new Riemannian symmetric spaces, and this is not a constant curvature space. Okay. And we are going to compute, or we are not going to compute, we are going to just write down today, since we don't have much time, I'm just going to write down statement of theorems and give proofs very rarely. Okay, so geometric facts on symmetric spaces. So we have connection. We are given a metric, and symmetric spaces arising from G, K, sigma, and P, Riemannian symmetric pair. We want to know formula for the, what connection, a nice formula which is computable for connection, for curvature. You might ask, what are the geodesics here? So these are all well known, and I'm going to write down one by one, and the proof is neither easy nor difficult. So, but it will take time, so I'll avoid giving proofs. So, but let me just write down. So, fact number one. So, one. So, I have, given a connection on, so let me just define, so this is a connection just have to say what is the minus n. All right, so this connection gives me this connection and a vector field and so this plus a vector field gives me a operator which is I denote by this by Lx minus x. This is a tensor. Okay. And what is Lx? Lx is the Lie derivative, and this is the usual. So Ax y is defined to be simply Lx y minus this y, which is xy minus xy. And since I'm taking I'm taking differences of two derivations, it becomes a tensor. Yeah, difference always becomes tensor because those certain things cancel out and it becomes F linear. It's very easy to check. And so, if one wants to know a formula for the connection, since one knows what Lie derivatives are, just formula for the connection is same as knowing this one, Ax, right? Because I know what Lie derivative, how to calculate Lie derivative, right? So, which is what I'm going to write for the symmetric space. So, all right, so before that I need some more terminology. So, when G is acting on a manifold M, G gives rise to nice vector fields on manifold M. How? So, given All right, so let me just say that for M in M, set phi M from G to M be the orbit map, be defined by what time phi mg is G for all. This is certainly a smooth map, and so I get, so given X in the Lie algebra of G, I can produce vector fields over M as follows. So set X star in, so define X star in gamma by X star of M to be d(I) M at identity of X. Okay, so I have the Lie algebra EG. I take a tangent vector and I have this point on which the M naught. I consider, so this is same as saying, so this is same as I consider the curve, say gamma M dot 0, where gamma M X, maybe I should just write mx t is defined by all t. So like this, I translate, I take a curve which is, and I take the tangent vector. So this is my assignment at the point M. So I consider the point X, take every point and consider this map, this curve exponential Tx is a curve in G, and I translate my point M by this curve. I end up getting a curve in M, and at each point I take such a curve and take the derivative at 0. Okay, so it gives me a vector. For every point in M, I'll end up getting a vector in the tangent space, and this gives me a smooth vector field. So that's an exercise that this is smooth. Okay. So this is a very general fact, and you can also prove that if I have the Lie bracket here, then this is going to be minus of xy. It is almost the so exercise 1, exercise 2. So it says that if the Lie algebra of the group to the Lie algebra of the vector field, this map is almost a Lie algebra homomorphism up to a sign. Okay, but the point is, if I instead of left action, so this is a left action. If I take the right action, then that minus sign will disappear, and this is going to be, so instead of so I take, instead of multiplying M from left, I multiply M from the right. Then you'll genuinely get a Lie algebra homomorphism. That minus sign will disappear. So this minus sign is appearing only because I'm taking left action. If you take the right action, it will disappear. So you'll get genuine vector fields. So there is a Lie algebra homomorphism from the group to the vector fields, you'll get a Lie algebra homomorphism if I take a right action. Okay, so now, yeah, absolutely. So yeah, so there's another fact that, vector field gives integral curves and flows. So what are the integral curves? So these are nice exercises of basic differential, manifolds and so on. So let me just also write down, maybe not here, maybe here. So I have this vector field x star on M. So any vector field gives me a flow and integral curve. So what is the integral curve? So let M be a point in M. So then gamma x, mx t is precisely the integral curve. So is the integral unique curve such that, x star gamma mxt is going to be gamma mx dot t. Okay, and gamma mx t is 0 is m. Okay, so this is, you can check this. So it needs a little bit of checking. This is the one you need to check. This is obvious. And what is the flow? So once I have a vector field, it gives, so in particular, this is a complete vector field. That means the integral curves are defined over whole of R. So this is for all. These are very special vector fields once you have a group action on a manifold. And also, you can check that the flow corresponding to XTM. So XTM is, I guess you know what a flow is. These are one parameter family of diffeomorphism corresponding to the vector fields. Okay, it sends a point, and at the time t, it sends a point to gamma mt, where t is gamma m is the integral curve passing through M. Okay, so this is simply left translation by exponential tx. So gamma star t is simply left translations by exponential tx. Okay, so at time t, at time 0 I have identity, at time t I am just multiplying every point by exponential tx. So these are basic things. So here is a formula that I'm going to write now. So what is Lx? So I have this situation P going to T, E, K, G mod K. So let's get back to the situation T pi. Okay, let's denote it by this. And this is an isomorphism of vector spaces. And this is the isomorphism which is K equivalent isomorphism. Okay, now so I consider, so let x, so then fact, I'm just writing the fact. So x in K, and then let Ax star d pi of y. So you see, I'm writing in terms of P, because I know what P is. I mean, this is kind of a, I understand this through P. So all my formulas are going to be written in terms of this map. Okay? Because I have a hold on what P is, and after all, I have defined everything. Locally, this is same on the tangent space. The inner product is also defined on this through P. So this is going to be d pi minus x y if y is in P. And this is enough because I need to only tell you what happens for every tangent space, and every tangent vector is d pi y for some y. Okay, so this is number one, and let x is in P, then a x star d pi y 0 for all y. Okay, this formula, this is not so difficult to prove, but I'm not going to prove it. So, so maybe I'm going to go from, so again I continue from this side. So I have this curve which are called gamma x ek, defined by x tx k. Okay, this x tx is the exponential in the Lie group. Okay, I have this curve, and then I have this parallel transport on this curve. So this is from 0 to t is simply the just multiplying this by this. Okay, so this is a fact number 2. Okay, the moment I have this, so this is for all x in P. This is a very important. So parallel translation along this very special type of curves are given by left translations. Okay, so once I have this fact 3 which says gamma x ek for x in P are the geodesics, is the geodesic such that gamma dot x ek 0 is d pi of x, and gamma, so this is the unique geodesic satisfying this property that ek. And how? Because this fact is immediate from fact number 2, because if I consider gamma dot x ek t, this is simply, we know that from very general fact that this is going to be d of L x dx of gamma, so d pi of x, which is the gamma dot at 0. So the derivative of this curve at the point t is the parallel transport. So it is the left translation. This is the left translation of d pi x. That's very easy to see. But we have by fact 2, this is the parallel transport k of x at 0 to t of d pi of x. And parallel transport, if I parallel transport any vector along a curve, the vector field that I get is parallel. Okay, so the derivative of this curve gives me a parallel vector field, which is equivalent to saying that this is geodesic. Okay, that means gamma x ek, okay, is geodesic. So gamma doesn't accelerate with respect to the connection that I'm given. Okay. So this is the description of geodesics. If I choose a point, so x in P, and I just consider x ek. Okay, and this curves. So this is going to give me geodesics. Okay. This fact that the parallel transport is at ek is just translation, left translation by exponential tx tells me that this connection that I get doesn't depend on the metric. Okay. So if I choose any other metric on P which satisfies add k invariance and so on, I'll end up getting the same connection. And why is that true? So suppose I have one metric here, I have one connection here, I have another metric. These are all on P. I get 2. Then what is this one? So I take V at T E K G mod K and let x star be such that x star of d pi, sorry, x star at ek is V. Okay. Then this one, V of y is going to be what? So, you know, when I'm given a connection, there's a formula for computing the covariant derivative at a point with of a vector field at a point. That is, I take any curve for which the initial velocity is v, and I take parallel transport of the vector at evaluate the y evaluated at that curve, and then take the derivative. This is precisely this. This is d by dt. So this is p. Let's take the curve to be gamma x here. So this is going to be gamma ekx. This is going to be t to 0 of y of gamma ekx. I consider this. So this is a vector in my tangent space at et, and I'm getting a one parameter family of vectors at the tangent space of P, and I take the derivative, and that's the formula for it. This is a well-known fact. This is very not so easy. This is a fact how one like computes the connection. I mean, this is easy. But this is d by dt is, what is this? This is simply left translations. L, G, L. I know that the parallel transport is just left translation, so this is exponential tx inverse d at exponential tx of y gamma ekx. So, but this thing L of x tx is giving me the flow of the vector field. That is for a very general situation when G is acting on M. So, and we know how to calculate Lie derivative. So this is going to be x star y at E. So the connection at the point V, y is precisely the Lie derivative of x star of y with respect to, nothing to do with the metric. Right? So at point identity, I have shown you that the value of the connection is same as the Lie derivative, and so it agrees at identity. So, and since my left translations are isometry, so these are affine maps. So these two connections agree everywhere. So this is a very important fact that the metric, whatever metric that you choose, you will end up getting the same connection. So the geometry remains the same. Okay. All right, so now, okay, the connection doesn't change if you multiply a constant to the metric, but the sectional curvature will change. Okay. Yes, let me just see what. Okay, so here is a very important formula, curvature formula. So I'm again in the same situation of G mod K, and the curvature tensor at identity K have this following formula: d pi e of x, d pi e of y, d pi e of z is going to be d pi e of minus x, y, z. For all x, y, z. How nice it is, right? So this is the formula, and this formula is going to play a very important role when we study, next bunch of things like. All right. This formula, the proof is not easy. Proof is non-trivial, and you can Helgason. Is a reference. This formula is going to tell me that using this formula, I'm going to give a formula for the sectional curvature, and that using this formula, one can see that the spaces of SL R mod S1 R, these are negative, positive curvature spaces. And variable is not constant. All right. There is a very important object, like analogous to the fact in the setting of Lie groups. So simply connected Lie groups and Lie algebras, these two categories are same, right? We have seen that given a Lie algebra over characteristic 0, I can group a Lie group for which the Lie algebra is, so I can get a simply connected Lie group and so on. Okay, Similarly, for classifying symmetric spaces, there is an algebraic category which are called orthogonal involutive Lie algebras. So what are orthogonal involutive Lie algebras? Okay, orthogonal involutive Lie algebras. I abbreviate by OILA. Okay. So G is a Lie algebra. S is an involution on the Lie algebra of order 2. And so when I'm given an involution, the moment I give an involution of order 2, the Lie algebra breaks up into plus and minus eigenspaces, and plus and minus eigenspaces. So K is X in G. So let this be out of G. Order of S is 2. So this Sx is minus X. P is, sorry, X is minus X. And this is obvious to check that this satisfies the following property, that K is a subalgebra. Kp is in P, Pp is in This is an absolutely easy fact to check using the fact that AC is a automorphism of the Lie algebra. So, and of course, G is direct sum of K plus P. Alright, so these are involutive Lie algebras. The moment I am given an involution, an automorphism of order 2, this pair is called an involutive Lie algebra. And what is orthogonal involutive Lie algebra? So, in addition to this information, if I assume that K in G is compactly embedded, and there is a inner product on P such that this is infinitesimally add K invariant. So which is add K G invariant infinitesimally. That means add X dot Y plus dot add X Y is 0 for all X in K or all on P. Then a quadruple GS, K and P is called orthogonal involutive Lie algebra. This is just the infinitesimal analog of Riemannian symmetric spaces. So like we do in Lie groups, we try to, when you classify Lie groups, you try to classify the associated Lie algebras. Linear objects are much easier to classify than non-linear objects. So similarly, here, when you want to classify Riemannian symmetric spaces, you want to classify these objects. So these objects, so given any symmetric space, I get a Riemannian symmetric pair, and from the Riemannian symmetric pair, there's an obvious way to get orthogonal involutive Lie algebra. So namely, you take the tangents. So Riemannian symmetric pair is GK, sigma, and inner product on P. So you take the tangent space at identity, the tangent space at K, keep the inner product same, and of course, if K is add K is compact subgroup of G, then so is going to be K is a compact Lie algebra, compactly embedded Lie algebra. So this is precisely this setup. And conversely, given any orthogonal involutive Lie algebra, you get a simply connected Riemannian space, Riemannian symmetric space. That means I'll just quickly say how, because so symmetric space Riemannian symmetric pair, I have OILA. Now from OILA, I am going to consider a simply connected Riemannian symmetric space. So I first consider G a simply connected group such that TEG is same as G. K is a connected subgroup such that Lie algebra of K, TEK is K, and so on. Okay? And next, what do we do? I consider G mod K. And notice that since K is connected, and if I start with the OILA, since I have compactly embedded, I assume that K is in compactly embedded, so add of K in GL of the Lie algebra is going to be a compact subgroup. Okay, all these things will automatically satisfy. And this all you just now see that I construct a Riemannian symmetric pair, I consider a corresponding symmetric space, and this symmetric space is going to be simply connected. Because my space, the group is simply connected, I'm modding out by a connected subgroup. So when I am a simply connected group and mod out by a closed subgroup, that is going to be simply connected. All right. So the category of symmetric spaces. So there is a version of a OILA being effective. Effective is same as saying that the maximal ideal of G which is contained in K is 0. Okay. The ideal of G, the maximal ideal of G which is contained in K is 0, which is analogous to saying that the maximal normal subgroups corresponds to ideals in Lie groups. Normal subgroups in Lie groups correspond to ideals in the Lie algebra. So here is the analog is the maximal ideal in K is 0. So I work with effective OILA. Okay, so we always assume OILA is effective. Okay. Now, a OILA is said to be a maximal OILA. So here is a definition. So GS, G1, S1, K, P is going to said to be a sub of G2, S2, K2, P if P1 is same as P2. If G1 is sitting inside G2, S2 G2 is same as, sorry, S2 G1 is same as S1 and P1 is same as P2. Okay. The P parts are equal. The G1 is the Lie algebra, G1 is sitting inside G2 and P, this one, the restriction of P2 is same as P1 and the involutive automorphism of G2 restricts to G1 to give me S1 and I assume that P1 is P2. So we have seen that, so the theorem here is simply connected Riemannian symmetric spaces are in one-to-one correspondence with the maximal OILAs, effective. I always assume it is effective. So these two categories are same. Products are products. I mean, if I take a product of symmetric space and you take a direct sum of maximal OILAs, they also respect the product. Okay. So now, in order to classify symmetric spaces, we want to classify what are OILAs. So here is a theorem. So if I start, okay, so another definition. So maybe I'll just write the definition here. So G, S, K, B, and OILA. It's called irreducible if add K, so K keeps P invariant, so add K P acts irreducibly on P. That means there are no proper add K invariant subspaces in P. Okay, so here is a final theorem about symmetric spaces. As far as the classification is concerned. So here, theorem G S K be an effective YLA, then so another definition here. An OILA is said to be an Euclidean YLA or flat YLA. This is called flat if PP is 0. Okay? And if it is flat, then the corresponding Riemannian symmetric space is flat. You can see that from the curvature formula. Okay? Because of this, and my P, everything is coming from P. So this is going to be 0. Okay? So this is going to be semi-simple. Is semi-simple called semi-simple if G is semi-simple. Semi-simple Lie algebra. Okay? So here is the classification of effective YLA. So G can be written as, so GS in the appropriate sense is isomorphic to G0, S0, direct sum, GI, SI, I run from 1 to N, where G0 is flat and these are irreducible semi-simple. Okay. And S, so these are ideals, these are all ideals. But the first one is flat and all of them are irreducible semi-simple. And what are irreducible semi-simples? So this tells me that I need to know what are irreducible semi-simples, right? Because these are all ideals. So irreducible semi-simple are of 3 types. So need to know GS irreducible semi-simple. All right. So here is the complete classification. G. So let us just look at another basic fact. So since I'm assuming irreducibility, so that means add K acts on P irreducibly. So I have 2 forms. One is a inner product and another is a bilinear form, namely the killing form restricted to P. Killing form, I guess, killing form is just, on a Lie algebra, killing form is trace of add X, add Y, okay? So I have an inner product that is given to me when I start with a YLA, and I have a killing form, which is also invariant. The irreducibility tells me that by Schur lemma, this is going to be C for some real C. So any inner product is going to be C times B, the killing form restricted to B. So here you can now tell what semi-simple irreducibles are. So one, C is greater than 0. G is simple and non-compact Lie algebra. Not just that, GS is a Cartan pair. That means I know what is a Cartan decomposition in a Lie algebra. GS is giving me precisely a Cartan decomposition when C is greater than 0. 2. If C is less than 0, then G is either compact, simple Lie algebra, or G is G1 direct sum G1 when G1 is a compact simple Lie algebra. So when this C is less than 0, it is always compact. When the C is greater than 0, it is simple, real simple Lie algebra. Compact simple Lie algebra. Okay. Now, so if you want to just translate this into symmetric spaces, you get what? You get the following result. That if I start with a simply connected symmetric space, and this is isometric to product of Rn flat metric and M plus and M minus. M plus is all the factors that are coming from non-compact irreducible YLAs, and M minus is coming from non-compact YLAs, and M plus is coming from arising from compact and non-compact. And there is a reason why I have written plus and minus sign. Here is the reason. So now you would like to calculate the sectional curvature. So I consider xy in P to be orthonormal, and my sectional curvature formula is d pi x, d pi y, d pi x, d pi y, comma this. And I have taken orthonormal, so the factor below is 1. And this is going to be R minus, I know my formula now, xy x, y. All right, minus and minus gives me plus, and so this is going to be q. Okay, since I'm using a lot of inner products, the inner product that I'm going to use on OILA associated to the Riemannian symmetric space is going to be denoted by q, and this is precisely this. X y. I hope I'm writing it right because I might goof up in. This is going to be C times B of just a second. This minus xy. Yeah. So this is C times, so I switch this factor and call it add of x of xy and add a minus sign here because I'm switching factor. And now bxy, this is a killing form, bxy is add x infinitesimal invariant. So I take this here, so this is going to be C times, so I have a minus sign here, I'm taking this here, so I again get a minus sign here, so this is going to be bxy, xy, I'm in a good shape. So this is precisely C times bxy, xy. Now, my xy is in P. So this implies xy is in K. Okay. But if you restrict the killing form on K, you get a negative definite inner product. Okay. So this quantity is always negative, no matter, negative, no matter what the OILAs are. Okay. So when I am in a compact group, C is negative. From that, I have written it here, maybe here. C is negative, so negative and negative gives me positive. So if I have a compact symmetric space, the curvature, the sectional curvature is positive. Similarly, C is positive when I have a non-compact symmetric space. In that case, this is negative. And since this is a negative definite form, curvature is 0 if and only if xy bracket is 0. So that means xy is commutes. Okay. So this tells me that it may have a variable curvature and the curvature is 0 precisely when the sectional curvature of the plane generated by 2xy is 0, precisely because when xy commute, or the geodesic exponential tx exponential ty commute. Okay. All right, so I am sort of very close to the end, but sort of conveyed some parts, but not fully. But let me just say at the end, what are totally geodesic submanifolds of symmetric space? So as far as total, so when the people are coming from symmetric space, dealing with symmetric space, and people who do pure Riemannian geometry, the notions vary a little. I mean, there is a subtle difference between the concept of totally geodesicness. Okay. For example, Helgason doesn't allow an open set of Rn to be totally geodesic. Okay. Or a open set in a subspace to be totally geodesic. Proper open set, Helgason doesn't allow. But the Riemannian geometers allow, because their definition is, if I have embedded isometric immersion of a submanifold inside Riemannian manifold, then the totally geodesic means the second fundamental form is 0. Okay? That is same as saying, if I have a geodesic at the bigger space, which is tangential to the manifold, it initially stays in the manifold. The entire geodesic may not stay. But Riemannian geometry, people like Helgason and so on, he wants the entire geodesic to stay. Also, there is a subtle difference. So, totally geodesic, so I'll of course follow Helgason because this is what I guess is important in this talks. So according to Helgason, a submanifold, a immersed submanifold is said to be totally geodesic if the geodesic, if I have a vector tangent to the submanifold and a point in the submanifold and a vector tangent, then the geodesic in the bigger space stays entirely in the submanifold. Okay, then he calls the submanifold totally geodesic. But that definition doesn't allow the one. So this is Riemannian geometer plus an extra condition is the totally geodesic submanifold for us. Completeness? Yeah, right. So totally geodesic in the previous sense, which is complete, then it is totally geodesic with respect to Helgason. All right. So totally geodesic submanifolds, they are classified completely with respect to a gadget called a Lie triple system. Okay. So what is a Lie triple system? S in G is said to be a Lie triple system if S is just a subspace such that S plus S, S, S is in S. Okay. This is called a Lie triple system. And so, how does totally geodesic submanifold of symmetric space are related to Lie triple system or classified by Lie triple system? They are classified by Lie triple system inside P. Lie triple system of G, which is sitting inside P. The subspace of P, which is satisfying this property. So this is same as saying, so I take the symmetry, I take that automorphism of, so let me just say that suppose I am given a Lie triple system, it gives me a Lie algebra. In fact, a Lie group which is invariant under sigma. How? So I consider S plus SS. See, SS is in K. S plus SS is going to be a subalgebra of S because of this property. This is a very nice checking exercise. S plus SS is going to be a subalgebra, and the moment I have a subalgebra, I take a Lie subgroup, not necessarily closed, but an embedded immersed submanifold. So G tilde, G dash gives me a Lie subgroup, connected Lie subgroup. Of course, since sigma is acting by -1, so this sigma keeps this invariant. So sigma keeps this subalgebra invariant. So sigma keeps this subgroup invariant. I take G dash of EK, the orbit of G dash, that's going to be a totally geodesic submanifold. And every totally geodesic submanifold appears like this. And why this is Lie triple system? Because of this formula. This formula involves 3 times, taking the bracket like this. So this is why. So you see, if I have a totally geodesic submanifold, the curvature remains same with respect to the submanifold of the manifold. So my curvature, if I start with 3 vectors here, the curvature tensor is same as here. It has to lie in the subspace. Okay? And correspondingly, if I have a Lie triple, so a group, so a totally geodesic submanifold gives me a Lie triple system, is easy to see. And once I have a Lie triple system, I consider this subalgebra and take the corresponding Lie group and take the orbit, that is going to give me a totally geodesic submanifold. So that's the proof. The totally geodesic submanifolds are precisely classified by Lie triple system. And last bit which I'm not, I want to tell you that any non-compact symmetric space is simply connected, in fact, diffeomorphic to Rn, because non-compact symmetric space, they arise from Cartan pair. So this gives me a Cartan decomposition, and once I have a Cartan decomposition, the group can be written as k times x of p, and that x of p is diffeomorphic to G mod k. So the group G mod k is simply connected, in fact, diffeomorphic to Rn. And that also follows from Hadamard theorem, because I have my curvature is non-positive. Okay, so we have two proofs of the fact that a non-compact symmetric space is always simply connected. And as I said, if the exponential map is a diffeomorphism, then we have a complete description of the symmetry, namely, you take minus identity and exponential inverse minus identity exponential. That gives me the symmetry. And finally, any non-compact symmetric space can be embedded inside SLNR mod SONR. Okay? So that follows from what I said, with the fact that a semisimple subgroup of, or reductive subgroup of SONR can be conjugated to be invariant under the transpose. So this is the theorem of Mosto, which says, if I take any semisimple Lie group of GLNR or SLNR, then there is A in GLNR, so that A inverse is invariant under transpose. That proves the fact that any non-compact semisimple group can be embedded as a totally geodesic submanifold inside SLNR mod SONR. I'll end there.